Today I want to present a solution to the Benelux Math Olympiad 2022 problem 3. At first, let's have a look on the picture. We are given an acute angle triangle ABC, and now we choose points B1, C1, B2 and C2 on the sides in the following way. At first you want to have that AB1 is equal to BB1, so B1 should have the same distance to A and B, and we want also B1 to be on side AC. In the same way, we choose the point C1 on AB in such a way that AC1 is equal to C1C. So C1 has the same distance to A and C. The last 2 points, B2 and C2, are chosen on the side BC in such a way that AB2 is equal to B2C, so B2 has the same distance to A and C, and in the same way C2 has the same distance to A and B. When we see a geometry problem where we have some given points, then it's always a good idea to at first think about how we can construct these given points. In this problem, this is not so hard because since B2 and C1 both have the same distance to A and C, we know that these 2 points must lie on the perpendicular bisector of AC. In the same way, we can construct points B1 and C2 if we draw the perpendicular bisector of AB and intersect it with AC and BC. Now, we haven't really started with the problem yet, but we already have a nice point, namely the intersection of these 2 lines. And here we get the point O, which is the circumcenter of triangle ABC, since these 2 lines are the perpendicular bisectors of AC and AB. Now, since we should prove that the points Z1, B2, B1 and C2 should lie on a circle, we are motivated to use the converse of the intersecting secants theorem for the supposed circle C1, B2, B1 and C2. So we want to try to prove that O B1 times O C2 is equal to O B2 times O C1. Here I want to note that since the triangle ABC is acute, we know that the point O, which is the circumcenter of triangle ABC, lies inside of ABC, and therefore the points B1 and C2 lie on the same side of O with respect to the perpendicular bisector of AB, and in the same way the points B2 and C1 lie on the same side of O with respect to the perpendicular bisector of AC. This means that the signs in this equation here are right, and therefore it is enough to prove this equation for the absolute values of these lengths. Now what we want to do is to write this product here in another form in such a way that the new form is symmetric in the points B and C. And then we are done, because then we can do the same thing for the left hand side. This motivates us to draw in the line AO, because the line AO is symmetric in the points B and C, and we also know that we can calculate some angles enclosed by the line AO. At first I want to note that this angle here is half of the angle COA, and COA is 2 times angle CBA, so this angle here is equal to angle CBA here. Moreover, we have right angles here, and therefore this means that the last angle in this small triangle here and in the big triangle here is also equal, so we get that this green angle here, which is B1 C2C, is equal to the angle here, which is OAB1. Moreover, since the point C2 has same difference to the points A and B, we know that AC2B is equilateral. Therefore, we want to draw in the line AC2, and here we then directly get that the angle AC2B1, which is this one here, must also be the green angle. Now we see that we have 2 equal angles, namely the angle OAB1 and the angle AC2B1, and therefore by the tangent chord theorem we know that the circumcircle of C2, B1 and A is tangent to the line OA. So let's write this down. From this fact here we can now conclude that OB1 times OC2 is equal to OA squared. So OB1 times OC2 is equal to OA squared. And now OA is symmetric in B and C, and therefore in the same way we can conclude that OA squared is also OB2 times OC1. So this is OB2 times OC1, and therefore we proved this equality here and we are done.